So, how's everybody doing out there? Well, welcome to day 6 of Corona Online School. So, hopefully, everybody did a good job with the addition and subtraction of whole numbers and got to make some nice little pictures and things to go with their stuff. So, and hopefully, everybody thought it was a little bit easier than the set theory stuff that we've been working on. So, today we're going to get into multiplication and division of whole numbers. And so, a lot of these are actually going to kind of rely on the fact that multiplication is just another way of thinking about repeated addition, and division is kind of a way to think about repeated subtraction. So, a lot of cases, even though it looks like it might be a multiplication problem, we may be doing just a lot of addition to actually get our answers. And so, again, the big things we want to focus on are not necessarily the answer is 5 times 3 or something like that. We want to talk about the model and how we can use the model to display the information. So if we look right off the bat, we've got our nice little definition about multiplication. Just like I had said, it can be thought of as repeated addition. And so in this case, the product of A and B, just written as A dot B. And there's technically a lot of other ways that you can actually write multiplication. So like A dot B is obviously one. You've probably seen like A times B with the little X. So they use that in middle school, or I mean in elementary school. They start to get away from it a little bit more in middle school just because eventually they're going to be introducing variables and they don't want you to confuse like the time signs with the variable. You could use parentheses, so like A parentheses B is another way that you can represent multiplication. And technically, like you can actually, if it's two letters and stuff, like you can just write them side by side with no dot, no parentheses, nothing in between. So any of those four things all represent multiplication for us. Um, so if we look, so again, A times B is just, B plus B plus B as many times as A is, where of course A is not equal to 0. And in our equation, A times B equals C, A and B are called the factors. So A is a factor, B is a factor, and then C is the product. So the actual multiplication of the two is what's called the product. So just like in addition, we had those properties of whole number addition. So notice we've actually got a lot more properties when it comes to multiplication. Now some of them are the same, so kind of keep that in mind. So if we look at the very first one, so closure property, so it's exactly the same as what we had for addition, except instead of being able to add two whole numbers and get a whole number, we're going to multiply two whole numbers and get a whole number. So again, only thing that could go wrong, which it won't for any of our cases, if somehow you multiply two whole numbers and you end up with like a weird fraction or a negative sign or something like that. So closure is usually pretty straightforward with the type of stuff that we work on, but it's good to know that that property exists. So commutative property, again, we had that for addition. So again, it doesn't matter whether you do 2 times 3, that's going to be 6, same as 3 times 2 is 6. So it doesn't matter which order you multiply them in, you always get the same answer. So associative property, so again, we had this for addition, so you can kind of rearrange how you multiply things and you'll get the right answer. So for example, if I do 2 times 3 times 4, so I would have to multiply the 2 and the 3 first because of order of operations. So 6 times 4 equals 24. Or if I wrote this as 2 times 3 times 4, so now order of operations tells me I have to multiply the 3 times the 4 to get 12. Then 2 times 12 again gives me 24. So again, you can kind of move these parentheses around, multiply in different orders and stuff like that, and you'll still get the exact same answer, which is good. So multiplication property of 1. So this is similar to our additive property of 0 that we had. So for addition, if you add 0 to anything, you always get the original number back again. So same thing's true if you multiply something times 1, you're always going to get the original number back again. So like 2 times 1 is just 2 in that case. So the next two are unique to multiplication. So in this case, we've got the multiplication by 0 property. And so that's just saying that if you multiply anything times 0, you're always going to get 0 as our answer. So 3 times 0 is 0, 4 times 0 is 0. So anything times 0 is going to be 0. And then the last one is the distributive property. And so this one, if you notice, it actually combines multiplication and addition both. So this is one of the only properties that kind of combines both of them together. And so the way it works is if I had something like 2 times 3 plus 4, then what I could do is I could either simplify the inside and get 3 plus 4 is 7. 7 times 2 gives me 14. Or what I could do is actually distribute the 2 first, in which case that'll give me 2 times 3 plus 2 times 4. So 2 times 3 is 6, plus 2 times 4 is 8, and 6 plus 8 gives me 14. So luckily they both worked out in this case. So again, it gives you a way that you can kind of pick and choose how you want to do these guys. So you can kind of do the addition first, then do the multiplication, or you can do the multiplication first, then the addition. So, all right. So does anybody have any questions or anything about any of the properties? All right, very good. So now let's kind of go through this list and see if we can identify which property goes with which example. So again, feel free to yell out your answer. I'll be listening. So 4 parentheses 3 plus 2 equals 4 times 3 plus 4 times 2. Oh, I think I heard somebody. Distributive property. Good. Very nice. So again, distributive property is going to be the only property that combines both multiplication and addition. So otherwise, these are always going to be either just straight addition or straight multiplication. So distributive property is the only one that has both. So keep that in mind. So 0 times 67 equals 0. So that's going to be our 0 property. Good. I heard somebody out there say it. So multiplication by 0 property. So I'm just going to call it 0 property. And I'll put multiplication to keep it separate from the addition property. So 3 times parentheses 4 times 11 equals parentheses 3 times 4 times 11. Associative. Yes, good job. You guys are fast. I can barely even get these done before you guys are shouting out answers at me. This is cool. All right, 8 times 9 equals 9 times 8. Commutative, good. One times 5 equals 1. So that's the 1 property for multiplication. Yes, good job. And then finally, 7 times 6 equals 42. And so that's just our closure property. So we multiplied 2 whole numbers together, and we ended up with a nice whole number as our answer. So that's just closure. All right, perfect. All right, so look those over. Make sure you definitely understand if there was some you were confused about or if you guessed something different. Let me know if you have any questions about it. Otherwise, let's get into some techniques of how we actually want to solve these different modeling problems involving multiplication and division. So if you notice, this time for multiplication, we have a ton of different possibilities here. So we've actually got, 6 different models that we're going to talk about. So I'm going to go through and demonstrate one of each kind just so you can get an idea. And so again, I'm not focused on like what the math equation looks like or anything like that. I want to do this straight from a model perspective. So in this first example, we've got Sally made cookies to share with her friends. Sally gave 5 cookies to each of her 4 friends. How many cookies did Sally give out to her friends? So in this case, this one's kind of crying out to me to do that repeated addition set model. So the fact that she's got 4 friends kind of tells you could make a circle for each one of those friends, and then we could populate those circles with the number of cookies and then just kind of count up what we would get from there. So again, even though this looks like a multiplication, ultimately when we get our answer, we're really just going to be counting up and adding. So in this case, I'm going to do repeated addition set model. And so in this case, I'm going to make a circle for each of her friends. And so I'm just going to kind of label them underneath because I don't know their names. Friend 1, friend 2, friend 3, friend 4. And so the idea is she gave 5 cookies to each of her friends. So I'm going to go ahead and draw 5 cookies to friend 1. You can get as detailed as these as you want. You can put chocolate chips in them. You can make them colored, whatever you want to do, whatever your favorite cookie is. So there's 5 more. And there's 5 more. So now Sally's giving away the 5 cookies to each of her friends. So now the goal is what we want to do is just kind of count how many cookies we've got in each circle. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it looks like Sally gave out 20 cookies in that case. And if you wanted, you could have combined these all together and made them into one big set and then drew all 20 cookies inside of them. Or you can keep them like I did in individual little sets, so that way I can kind of distinguish between the friends and how many each one got. But, all right. So if you have any questions about that, let me know. So let's look at example 3 here. So example 3, John walks to school and back 3 miles a day. How many miles does he walk to and from school in a week? So in this case, so again, we're going to assume that in this case, school is just 5 days. So let's assume, and he's obviously not doing online school because otherwise there would be no reason to walk to school. So he's obviously somewhere where they've allowed kids to go back to school. So in this case, we're going to think of this as 5 days, and we want to walk 3 miles a day. So again, just like with addition, anytime we were doing kind of a distance or something like that, I like to use the number line approach. And notice our second thing is repeated addition measurement number line. So I'm going to use the number line model for this. And so let me start off with my number line here. And so again, since these are all whole numbers, I know I can't have anything smaller than 0. So I'm going to start with 0 on the left. And then I'm going to start laying these out. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So if we have enough room here. All right. And so he walks to school and back 3 miles. So in one day, he walks 3 miles. So what I'm going to do is I'm going to make just a different color for every day. So in this case, I'll do starting at 0. Day 1, we walked 3 miles. So maybe this is Monday, and we walked 3 miles. And then Tuesday, let me change colors here. So Tuesday, we'll make that orange. So again, we jump another 3 miles. And then let's make Wednesday red. So again, jump 3 more miles. Let's make this weird lime green or whatever. Thursday, so 3 more miles. And then finally, let's do blue. 3 more miles. So there's Friday. So the nice thing about the number line method is when you're done at the very end, like wherever your last jump is, that should be your answer. Now you can go back and confirm, I had 3 plus 3 was 6, 6 plus 3 was 9, 9 plus 3 was 12, and then 12 plus 3 was 15. But the good thing is the measurement kind of lands us on the very last spot and we know how many miles that they've walked. So in this case, John walked 15 miles in a week. All right. Sound okay with everybody? All right, perfect. So again, if you have questions, pause the video, ask me. Don't keep moving on if you're not sure about some of these techniques. If I'm going too fast or anything like that, definitely let me know also. Otherwise, let's move on to example 4. So example 4, in her garden, Anne planted 5 rows of beans, each containing 9 seeds. How many seeds did Anne plant? So this one is actually, the way they describe it is what they're calling an array method. But I also like to think of it as a picture method. So an array, think of it as like almost like a matrix or something like that. And you could have numbers in them. I like to draw mine with like actual pictures and stuff like that. So I'm actually going to call this array / picture or diagram, because that's the way I see this problem more anyway. So what I've got is I've got Anne planted 5 rows of beans, and then each row contained 9 seeds. So what I'm going to do is I'm actually going to lay out what I think her garden would actually look like in this case. So I'm going to go through and make a big rectangular plot of land here for her garden. And then what I'm going to do is kind of like put some little dotted lines in here just to represent the rows for me so I can distinguish the rows from each other. So in this case, there's my row 1, there's my row 2, there's my row 3, and then this dotted line is going to give me my row 4 and 5. So now what I want to do is actually put the seeds in each of these rows. So I'm going to make the seeds some other color here. Let's make them brown, say. So in this case, there should be 9 seeds in each row. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I want to do that same thing over again. So again, I'm going to get 1, 2, 3, 4, 5, 6, 7, 8, 9. So now I've got row 2 planted. So let's plant row 3, 2, 3, 4, 5, 6, 7, 9. So row 3 is planted. 1, 2, 3, 4, 5, 6, 7, 8, 9. So row 4 is planted. Finally, row 5. 1, 2, 3, 4, 5, 6, 7, 9. Good. So now we've actually got our garden all laid out. We've got it nice and neat. We've got all of our rows arranged. So now again, even though it's a multiplication problem, how are we going to get our answer? Well, we're just going to count these guys up. And so, and again, you can count this multiple ways. Like if you wanted to count the number of rows and then just kind of, double them from there, you could do that. Or you could just physically go through and count each and every bean that we planted or seed that we planted. So in this case, we're got 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got 9 here, got 9 here, got 9 here, got 9 there. So I could go through and kind of do, so that gives me 18, that gives me 27, 36, and then finally 45. Or again, you could physically just go through and count all 45 seeds that we planted and go from there. So in this case, it looks like Anne planted 45 seeds. All right. Is that okay with everybody? So everybody okay with the array / picture diagram version? All right, perfect. So let's look at, let me change colors here. So let's look at example 5. So John wants to order tiles for an entrance that is 3 feet by 5 feet. The tiles are 1 square foot each. How many tiles does John need? So this one, what we're going to do is what's called the rectangular area model. And so what I'm really going to do is actually try to draw what this living room would look like and actually put the tiles in there and then actually just count how many tiles we had to use. So let's kind of write this down, rectangular area. So the first thing I'm going to do is I know I need to make a rectangle that's approximately 3 feet by 5 feet. So again, do your best to draw this so it looks halfway decent. So, mine never looks that good. I'm sure your guys always look better than mine. And so now what we want to do is we need to divide this 3-foot section by 5-foot section into a bunch of 1 foot by 1 foot tiles is the idea. So in other words, like what we're really trying to do is we're trying to basically say, okay, here's a 1 foot tile, here's a 1 foot tile, there's a 1 foot tile, and then figure out how many of those we're going to need to fill up this actual space. So what I'm going to do, instead of kind of keeping drawing it this way, just because I might mess it up, is I'm going to take the 3-foot side and divide it, kind of like I did the array method, into 3 equal rows. And then I'm going to do the same thing with the 5-foot section and turn those into, as even as I can, 5 1-foot columns in this case. So in this case, for the 3-foot section, I need 2 lines to divide this into 3 1-foot rows. And in the 5-foot side, I'm going to need 4 lines to turn these into 5 1-foot rows or columns. So let's see. So I've got a 1, 2, 3, and a 4. That wasn't too bad. Look at that. Pretty even. So now, not only do we actually get to see kind of what the floor would look like tiled in, we can actually tell how many tiles there are. So again, we're not really multiplying. We're just going to kind of go through and add how many tiles did we actually lay down. So in this case, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So in this case, in order to John to fill his entryway with tiles, he's going to need 15 1-foot by 1-foot tiles in this case. So John needs 15 tiles. All right, I love this section. There's all these cool pictures we get to draw and stuff like that. I mean, it's so neat. And again, feel free to be creative, colorful. If you want to color your tiles in, like make them different shapes, whatever you want to do. I mean, go wild with it. All right, so next one on our list is example 6. So Anne has a box of flags that contain 4 different colors. She has a blue flag, a yellow flag, a green flag, and a red flag. How many ways can she display 2 flags of different colors on the flagpole? So be careful there. The different colors is important. So what that means is she can't have like a blue flag with another blue flag because she doesn't have duplicate flags. So she could do like blue with yellow, blue with green, and blue with red, but she can't do like blue with blue or red with red or anything like that. So this one, what we're going to do is what's actually called a multiplication tree. And if you don't remember these, you probably have done them a long time ago. And so we're actually going to do them again more in the class related to actual numbers and stuff like that. So this one, I'm going to try to draw it as best as I can, but I'm sure I'll butcher it up some, but I'll do as good of a job as I can because this gets a little unwieldy at times. So what we want to do is we want to think of each of these branches as kind of a location of the flag. So notice, because with the flag, let me draw my little flagpole over here. So let's say we had the blue flag on top. And then maybe we had the, red flag underneath. So technically now that's going to be a different combination than if I do red on the top and then blue. So I want to be able to account for both of those. So what I'm going to do when I lay out my multiplication tree, I'm going to have like the first part I'm going to make, say, the top flag, and then the second set of branches I'm going to make be the bottom flag. So in this case, I know the difference. So in this case, I'm going to have a top flag and a bottom flag. And so the idea is for the top flag, I can choose any flag that I want, because at this point I haven't put any flag on the flagpole at all. So that means I've got a choice of blue, yellow, green, and red. So I can choose any of those guys for my top. So what I want is I want 4 branches off of this first section. And so from there, I'm going to say, let's let blue be the very top branch here. Then yellow be the second. Green. And red. So I probably should put these in different colors, but hopefully you'll get the idea. And then from there, my next set of branches is going to be the bottom flag. I knew I was going to run out of room. Ugh. And so the idea is, one of the flags have already been chosen on this branch. So for example, for this guy, blue's already been chosen. So I don't need 4 branches off of here because I'm not allowed to reuse blue. So that means I only need to have 3 branches off of this side. So I need 1 for yellow, 1 for green, and 1 for red. And so similarly, I can do the same thing for yellow. So for the yellow branch, we can't use yellow because it's already been used. So again, I only need 3 branches. So that means I need a branch for blue, I need a branch for green, and I need a branch for red. So now same thing for green. So green's already been used, so I can't use it again. So I only need 3 branches. So in this case, I need a branch for blue, branch for yellow, and a branch for red. And then finally, down to red again. Can't use red again, so I only need 3 branches again. So I need a blue and a yellow and a green. And then the idea is, if we go through and actually count the number of branches that we end up with, that'll tell us how many different flag combinations that we have. The other nice thing about this is you can actually kind of see what they would look like, because like here I can see I've got blue and yellow, blue with green, blue with red, yellow with blue, yellow with green. So you can kind of actually walk through and physically imagine what the flags would actually look like. So even though it takes a long time, that is one of the nice things about the multiplication tree. You get to see every single possibility that's available. So now let's go through and add these guys up. So I've got 1 branch, 2 branches, 3 branches, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got 12 branches total. So it looks like Anne can have 12 different flag combos. So basically she could hang these flags up, different 12 days in a row before she'd have to start having to repeat, is the idea. All right. Is that okay with everybody? All right. This might be a long video, so at any point in time, if you need to pause it, take a break or anything like that, feel free. I'm sorry if it's long, but I want to make sure you guys get these different techniques down. So again, take a breather if you need to, stop for a little bit, whatever you need to do, and then come back and recharge and be ready. All right, so last one. So this one's, we've got Bob's Sandwich Shop has a choice of white or wheat bread, a choice of ham, turkey, or roast beef. How many types of sandwiches can be made? So in this case, we're letting B be the set of breads. So in this case, we're calling X white bread, and we're calling Y wheat bread. And then for M, the set M, we're calling like the different lunch meats. So in this case, we've got H, T, and R. So where we've got H is ham, T is turkey, and R is roast beef. So in this case, what we're going to do is what's called the Cartesian coordinate system, so a Cartesian product. And so this is kind of the same thing as like an ordered pair. So if you remember ordered pairs from algebra and stuff like that, like 0, 2. So that's what we're doing. So we're just going to make an ordered pair. Unfortunately, ours aren't going to have numbers. They're just going to have a bunch of different letters. but it's going to give us a way to represent all the different sandwiches. So again, kind of like the multiplication tree, the nice thing is with this method is we'll be able to see every single sandwich type, even if it's in ordered pair form. So let's call this Cartesian product. And so what we want to do is actually kind of write these in little ordered pairs. So I'm going to put parentheses in here for each of these guys. And you can write them either way. For me, I'm going to put the bread first just because it's on the left-hand side. So in this case, I'm going to put X as the bread. And since we're in the ham column, then we're going to pair this up with a ham sandwich. So basically, this first ordered pair says I've got a ham sandwich on white bread. So that's what that ordered pair actually means. And so in this case, I'm going to go ahead and do all the white bread all at the same time. So again, I'm going to get my X in the front. Since we're in the turkey column, that'll give me a T as my second ordered pair. So again, what that X comma T means in words is I've got a turkey sandwich on white bread. So now again, let's finish off the white bread. So we'll get X comma R. So again, that means we've got a roast beef on white. So we've gone through all the different white breads. So now let's start back over with wheat. So wheat's going to be Y. And so again, since it's in the ham column, we're going to get Y comma H. So again, this means we have a ham sandwich on wheat bread. And then for the next one, so again, we're still using wheat bread, but we're in the turkey column, so we're going to get Y comma T. So this represents a turkey sandwich on wheat. And then finally, last one, we've got Y is still our wheat bread. R is our roast beef. So Y comma R gives us a roast beef on wheat. And that's our final possible sandwich that we can make using these 2 different types of bread and 3 different types of meat. So again, just like we did with the multiplication tree, now we just want to go through and kind of count each little box. So in this case, we've got 1 type of sandwich, 2 types of sandwiches, 3, 4, 5, and 6. So it looks like you've got 6 choices of sandwiches. At Bob's Sandwich Shop, in that case. All right. So very good. So hopefully everybody did pretty good on those guys. So again, if you need a little bit of a break, so we're getting ready to do division next. So luckily there's only 2 of those, so it shouldn't be quite as tiring. But again, if you need to pause this thing at any time, take a little break, come back to it and stuff. I'm sorry if it's long. But again, I just want to make sure you guys really get this stuff down. So let's go ahead and talk about division here real quick. So again, we've got our nice little definition for division. And so again, there's a few different ways you can actually write division. So in the first case, we've got A divided by B equals C. So we've got kind of our normal division sign that we see. So we can write it in this kind of slash form, which is kind of another way to write a fraction. That's just kind of a way to sideways write a fraction. And then we've got kind of our regular old fraction form, A divided by B equals C. And so in this case, just like with the subtraction, each part of the division had its own separate name. So did the subtraction. So division will be the same way. So like in this case, the A is what's called the dividend. So the top number is the dividend of the problem. And the bottom number that's being divided into it is called the divisor. And then the overall division itself is called the quotient. So C would be the quotient in this case. So the next one is very, 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 very important. And so this kind of messes people up sometimes. So if I've got something like 0 over 5, hopefully you recognize right away that that answer is 0. And if we try to do the division, we'll see why. So in this case, if I do the division on this, the 5 would go on the outside, the 0 would go on the inside. And it asks me, how many times what do I have to multiply 5 by to get 0? Well, the only way you can get 0 is by multiplying by 0. So 0 times 5 gives me 0. 0 minus 5 equals 0. And so lo and behold, 0 is my answer, and everything looks good. But what if I have something like this, 5 divided by 0? What if I put the 0 on the bottom? What happens? Well, again, if we wrote this out as a division, then what we're saying is what number can I multiply by 0 that's going to give me 5? That's right, nothing. So, because unfortunately, anytime I multiply something by 0, it's always going to give me 0. So I'm never going to be able to multiply something by 0 and get 5. So when this happens, what we say is that this fraction is undefined. It can't exist. If you try to put it in your calculator, it'll probably blow your calculator up. It just doesn't like it or anything like that. So kind of keep that in mind, that if the 0 is on the top, everything's fine. Your answer is 0. If the 0 is on the bottom of a division, the answer is undefined or does not exist in that case. All right, and so the last part, we'll get into this more later. Like, we won't do much of it in this section, but just kind of to let you know that sometimes when you divide things, you don't always end up dividing in evenly. So sometimes we'll end up with a remainder, which means that we've got some stuff left over. So just kind of keep that in mind. So like if I take 3 and divide it into 15, 3 goes into 5 15 times. In that case, I didn't have anything left over, so I ended up with a 0 remainder. But if I would have divided 3 into 17, well, still 5 goes into 3, or 3 goes into 5 15 times. But in this case, I had 2 left over. So sometimes we will see that happen, like if you're trying to divide up a bunch of cupcakes evenly or cookies evenly or something. If the people didn't bring the right amount, you may end up with leftover cookies in that case. So that's what we'll have when we have leftovers. That'll be our remainder in that case. So, all right. So if you have any questions about the definitions or anything, please let me know. So otherwise, let's look at these two different division models. Now these are weird because sometimes the way you draw them, they don't necessarily look that different, but they are subtly different. I mean, because one of them's repeated subtraction and the other one's partition model, and I'll try to describe how I'm drawing them. But again, like sometimes you won't necessarily recognize the difference between them. But all right. So let's look at example 8 here. Mr. Hall made 30 cookies and wants to sell them at the bake sale. If he puts 3 cookies in each baggie, how many bags of cookies can he sell? So in this case, what we've got, this one's actually kind of this long repeated subtraction, division by grouping. So I'm going to think of it more as division by grouping rather than repeated subtraction. It is repeated subtraction, but the way I'm going to arrange it is more by grouping. And the reason it's this way is because I know how many cookies I have. I know how I want to divvy them up, but I don't know how many bags I need. And so in this case, notice the number of groups is unknown. So in this case, the group would be how many actual bags I need. So I know I've got 30 cookies. I know I want to put them into piles of 3, but I don't know how many sandwich bags I'm going to need to actually put these cookies into. So my group is actually unknown in this case, the number of groups that I need. So the group size would be the number of cookies. So that's actually going to be the next problem in this case. But, all right. So what I want to do is actually kind of just start putting these into groups of 3 until I run out of 30 in this case. So there's cookie 1, cookie 2, cookie 3. So there's 1 bag that I'm going to need. So cookie 2 or cookie 1, cookie 2, cookie 3. So there's my next bag that I need. So cookie 1, cookie 2, cookie 3. Next bag that I need. And notice we are doing repeated subtraction because hopefully I'm kind of keeping track so I don't keep adding cookies past how many cookies I actually have. So in this case, let's do 3 more cookies. So in this case, I'm down to, let's see, well, let's actually reduce these as we go along. So the first set took me down to 27. The next set took me down to 24. Now I'm down to 21. Let's see, so now I'm down to 18 left of cookies to distribute. So let's do 3 more cookies. So that takes me down to 15. 3 more cookies takes me down to 12. 3 more cookies takes me down to 9. 3 more cookies takes me down to 6. 3 more cookies takes me down to 3. And then finally, this should be the last bag of cookies that I need. So I'm down to 0. So now I go back and count how many groups that I needed, or how many bags. So in this case, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case, it took me 10 groups, or 10 bags, to fill up these different cookies. So I needed all right, so that's our repeated subtraction, division by grouping, number of groups unknown. So again, hopefully that makes sense to everybody and everything's okay. So let's look at number example 9 here. So Mr. Thompson made 20 cupcakes for his class. If he has 10 students in his class, how many cupcakes can each student get? So in this case, we actually know the number of groups. So in this case, the 10 is how many groups we have. So think of those as the number of bags we had in the last class. But the problem is we don't know how many cupcakes each student is going to get. So we don't know kind of like what would be going into that bag. So that's why this one's slightly different than the one above. So this one we're going to do the partition model, or division by sharing. And so what I'm going to do for this one is, in this case, since I know how many like bags or how many groups I have to start off with, I'm going to go ahead and actually draw those first. So I'm going to actually, instead of drawing them as boxes like I did above, I'm going to actually just draw them as little people here. So I'm going to draw 10 little stick figures. So again, feel free to get creative, draw your fancy people if you can. I'm barely able to draw a stick figure, so don't be laughing at me at home too much. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect, look at that. So there are my 10 groups. So now I need to know how many things go inside of each group. In this case, inside each student's belly, because they're going to eat 2 cupcakes each. So what I want to do is I want to distribute them like one at a time until I actually run out, is kind of the idea. So in this case, I'm going to go around and give one, because in case I have more cupcakes than I have people, I don't want to give some people 3 cupcakes and put some people 2 cupcakes. I want to make sure everybody gets the same amount. So I'm going to distribute them individually rather than just handing them all out in the beginning. So in this case, there's 1 cupcake. There's 1 cupcake. So I'm just going to go through and give each person 1 cupcake first. So at this point, everybody's gotten a single cupcake. And that reduces me down to 10 cupcakes left. So that means I can start divvying out another cupcake to everybody else, because I know I've got enough to share. So in this case, I'm going to put a cupcake there, 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 cupcake there. So there was 10 more. So now I've reduced all my cupcakes down to 0. Everybody's gotten a fair share. And so ultimately, how many cupcakes did each student get? So in this case, we're just basically looking at any one individual student, because they should all have the same amount. And so each individual student received 2 cupcakes in this case. So each student received 2 cupcakes. All right, perfect. All right, so that's it for addition or multiplication and division. Again, I apologize for this video being so long, but again, I wanted to make sure you really got the techniques down. There's a ton of problems to practice in this case. I think there's actually 13, 16, some crazy amount. Now, there is some stuff at the very end that I'm going to let you guys try on your own. So it involves some exponents and rules of exponents. If you're struggling with it, let me know early, and I can make a little quick video separate of this one to kind of help you with these guys. But if you wanted to try them on your own and see how you do that, would be fine too. I didn't want to add it to this video because I knew this video was already going to be long. So try it in class tomorrow. If early on you're struggling and can't figure out what to do, I can make a quick video and upload it just to let you know. But I wanted to kind of keep this one just related to models, not anything other than that. Otherwise, good job. Ask if you have any questions, and I will see you guys tomorrow.